Hey everyone, this is Mr. Hausman. We're going to take a look today at the application of something that we've talked about already in class, and that topic is conservation of charge. So, anytime you have a quantity that is conserved, that you do not gain or lose any. The only thing you can do is rearrange that quantity. So chemical reactions, the mass of the reactants comes together. They rearrange the chemical bonds, and the mass of the products always equals the mass of the reactants. Well, when it comes to charge, we're going to talk about how the Q initial total has to always equal the Q final total. But we'll talk about how to know how to share those charges. And it's much simpler because it's not a chemical process, it's a physical movement of charge. So let's begin with three identical conducting spheres. They each have different charges. We've got Q1 has a charge of negative 16 microcoulombs, Q2 is 0, and Q3 is positive 10 microcoulombs. Now, why micro? Well, micro, of course, you may remember, is times 10 to the negative 6th. It just simply means that it's a small amount of charge. And as it turns out, a small 4 or 5-inch metal sphere can only hold so much charge because of the size of it. And so the typical amount is in the microcoulomb level. In fact, if you had 1 coulomb of charge, it would be an enormous amount of charge. And we'll get back to knowing how to measure that shortly when we do Q calculations. So really large. How much space would it take to have a whole coulomb of charge? Typically, that's the size of like a lightning cloud, has coulombs of charge in it. So much, much larger. Okay, so if someone said, what's the total charge of all three of these at the beginning, you'd say negative 16 plus 0 plus positive 10 gives you a total Q initial of course, negative 6 microcoulombs. But they're not touching each other right now, right? They're just sitting there on insulating bases, so they have no reason to move their charges. So what happens is a series of events. This is like a timeline. And when they physically come together, so in the very next picture, like a cartoon sequence, A touches B. So the negative 16 touches the 0. And when that happens, because they are the exact same size sphere, they have to share that charge. So you take the total of those two, negative 16 microcoulombs plus 0, divide it by 2, and you're going to find out that A and B acquire a charge of negative 8 microcoulombs. Sphere C never touched anyone. It's on an insulating base, so it remains positive 10 microcoulombs. Now, since they're all microcoulombs, we can kind of skip the unit for a minute, and then at the end we'll bring it back. So now A and B separate from each other, but they're not grounded, so they hold on to their charge. Okay, time keeps going. Well, now B is put into contact with C. Maybe someone pushes them together. So what do you get for a total charge when you have negative 8 plus 10? And the answer is, of course, positive 2. But then you have to share it because there's 2 of them. And so you get a positive 1 and positive 1. So it couldn't be any sort of, I don't want to say insultingly easier, if you just remember that when two spheres conduct, they distribute the charge evenly if they are the same size sphere. But what it's proving when we get down to the end, right? Now B and C are separated from each other, but they're not grounded. Now let's put our unit back on, microcoulombs. So we have a final of negative 8, a final of plus 1, a final of plus 1. And if someone said, what's the total Q of all three? Negative 8 plus 1 brings us back to the same total charge that we started with. So I'm going to ask you to do the next one on page, which looks the same, but it has different initial cues. This is a pretty easy skill. You can hit pause if you'd like in the video. I will provide the final answer at the bottom, but I won't show the steps along the way. And if you got all the way through, you discovered that A comes out to be -3 microcoulombs, B is -1.5 microcoulombs, and C is -1.5 microcoulombs. And so many people have told me over the years, you're like, I don't think that's allowed to happen. You can't have 1.5 charges. And the reason why that's totally allowed is because, remember, that's not how many electrons are on the sphere. It's a charge quantity. So it would be 1.5 times the elementary charge, and that is totally allowed to happen. So the Q final here, -3 plus -1.5 plus -5, the Q final is equal to -6. And 8 plus -14, my Q initial total was -6. And that's just a coincidence between the two problems. The actual distribution is, of course, totally different, but it just happened to be that our two sample problems had the same charge. So that's the extent of being able to look at and understand conservation of charge. But it's really important to understand this sharing or redistribution when two identical size metal spheres come together. So, okay, here's an introduction to measuring charge. So let's go back and remember some of our variables. Q stands for the charge of an object. It's measured in coulombs, sometimes microcoulombs, but the unit is coulombs. N, well, that's a counting number. That's the number of particles. And then there's E. And you say, oh, E stands for electron. Not when we talk about quantitation. This refers to the elementary charge. And if you think back to a few days ago, we found out that the elementary charge is always equal to positive or negative 1.6 times 10 to the -19th coulombs. Positive if it's the charge held by a single proton, negative if it's the charge held by a single electron. Now, how do we examine charges that are changing? Well, I will definitely introduce this formula. Q is equal to N times E. If someone just said find the charge, if you know the number of particles, you multiply that number of particles times the elementary charge, and someone would have to tell you whether you're counting electrons or protons. So sometimes you'll see me write this as times, let me actually make this a little neater, N times positive or negative E. That doesn't mean add and subtract. It means E can either be positive or negative. So that's how you simply measure Q. If you're trying to measure the change in Q, I tend to use, it's related to this formula, Q final equals Q initial plus or minus N times E. Now, how can a formula have plus or minus? Well, essentially, it's about gaining or losing charge. So if you are gaining, you use the plus operator. If you are losing, you use the subtraction sign. Just think about what it means. You know, gain is an additive process, and losing is negative. So let's take a look at our first sample problem. A neutral sphere, so that means my Q initial, my starting charge is 0, gains 2,000 electrons. Oh, that's 2,000 for my N value. And notice that I also am going to be using an elementary charge of -1.6 times 10 to the 19th coulombs. Negative because it's electrons that we are gaining. So what's the final charge? Well, the formula I prefer to use and teach people is Q final equals Q initial. Now, which sign do I use? Well, it clearly said in the given that it gains 2,000 electrons. So my Q initial is 0 because it started off neutral, and I'm going to gain 2,000 times -1.6 times 10 to the -19th coulombs. And you get a final charge of -3.2 times 10 to the -16th coulombs. Final answer. It's 2,000 times the elementary charge. And if you're a little rusty on scientific notation in your calculator, let me know. I can help you get through that, but most of us have used that on and off through chemistry and now physics. Okay, let's do the next one together. It starts off again neutral, so my Q initial is 0 coulombs. Now I lose, there's my important word, lose, N equals 3,000. But my elementary charge is going to be equal to negative 1.6 times 10 to the negative 19th coulombs because I'm dealing with electrons. So what's my final charge? Q final equals Q initial. Now I'm losing, so I'm going to subtract N times E. So my Q final is going to be equal to 0 minus 3,000 times negative 1.6 times 10 to the negative 19th coulombs. I think due to a recording glitch, I might have had my audio off. But I've set up number 3, and in this case, the problem had a known charge of negative 3 times 10 to the negative 6th. Because it's a negative coefficient, we know that there must be extra electrons. And here's where you use you don't have to use a delta Q or a Q final and Q initial. You just want to know what the charge, you know the charge and you want to find N. So when you set it up and you put in your Q and your elementary charge for an electron, the N comes out to be, and it does come out to be, a kind of rather large number. Make sure you're using your calculator right. But you come out to have, if you have that charge, you have moved 1.88 times 10 to the 13th electron. Oops, wrist hit that. So N can be an enormous number of electrons when you're talking about real-life charges. Even microcoulombs carries that many extra electrons. I'd like you to work on the bottom of this page. We're going to call this the Introduction to Q Problems. Some of you will be able to master it in the first go-around, but there will be a second day where we work on the subsequent pages, which are the same, but different. This is a case where getting familiar with this quantity, these units, will have a big impact when we start doing calculations in circuits and when we start doing even calculations in electric fields. So continue with page 15, and I will be certain to post the solutions. So good luck.